Pictorially, the Kalman filter looks like this. Nice Gaussian. I don't know why I'm drawing this, it's already here. A Gaussian, I'll circle it. We start off with that Gaussian. We then have the linear prediction part, which does the shift. We then say, but wait a minute, there may be some noise, so things get widened. We take our measurement and we sort of blend. Remember, it was that the Kalman filter is a blending between your prediction, which is what our prediction here was, and your measurement, and it creates a new estimate that's a weighted average between those depending upon the relative uncertainties. And the uncertainty gets smaller after we take the measurement. So uncertainty gets bigger when we do our prediction because we don't know exactly what happened, and then it gets smaller again when we take the measurement. We said nice things about it was that it's simple, it's compact, it's efficient, and it's very easy to spell. The cons of it are, in fact, maybe I should have listed these in the other order. Here it says, we'll say there's sort of a restricted class of motions defined by the linear model. The linear thing we can get around by using what's called an extended Kalman filter. A much bigger problem is it's got this nice unimodal distribution assumption. You're assuming the world really is a nice Gaussian of some uncertainty. And the question arises, what would you do if things are not a Gaussian? So what's an example of when you might need a non-Gaussian situation? Well, you remember these videos? Okay, and again, this comes from the Izard and Blake condensation tracking paper. There's all sorts of dynamics going on here of things jumping around. Let's see if I do that again. Yeah, there she goes. And things move quickly. They may be able to be nice and smooth sometimes. Then something rapid will happen. So like when the leaves are blowing in the wind, for a while they blow nicely. But basically, the problem here is that things are moving smoothly, and then all of a sudden you'll get a perturbation. And you'd like to be able to keep track of that. So graphically, we're going to show that like this, okay? So now we have the same model that we had before, okay? We have an estimate from the last time. We have a deterministic shift. We apply some smoothing because we grow the uncertainty, and then we take our measurement and we update our estimate. But now, these are not Gaussian lumps, right? These are sort of arbitrary distributions. And in fact, this particular figure is taken from the paper that introduced the particle filtering that we'll talk about in a minute to computer vision, that condensation paper I just mentioned.